A limit cycle for a system of differential equations is a closed integral curve. For example, a closed integral curve that has the property that it attracts or repels nearby integral curves. So we can draw some nearby integral curves. So if I have a curve from, and if it attracts, for example, from inside or from outside, if you have another integral curve that being attracted by this, then it is called stable. Otherwise, it is unstable. So when we look at limit cycles, we also want to discuss stability. Limit cycles can be stable or unstable. A given system of differential equations may not have any integral curves, limit cycles. So we will today look at some differential equations that have limit cycles, and then discuss stability of the system. So here is a system of two equations. Let's assume we have the derivative of x, which is some expression of xy. The second equation, the derivative of y, is an expression also of xy. So we will look at a system of two equations and then try to do some analysis of equations of this form. Here's an example. So in this example, we assume here P is specifically this expression. dx dt, the P is given as this expression. And the Q, so if we write the second differential equation, the derivative of y, which is also equal to the expression depending on xy, so we have negative x plus y minus x squared minus y squared. So this system of two equations, here we see very specific expression, right, given as the P function. So the Q function is also specifically this one, negative x plus y times this parenthesis. So for this particular system of two equations, we notice it is autonomous and nonlinear example. And we also notice that if we use polar coordinate system, possibly we can reduce the system. So let's for this system of two equations, we let x be r cosine theta, y r sin theta. That means we're going to do a change of variables. The equation of x, y will become equations of r theta. So by the polar coordinate system, you see we have, we will get two equations of r theta. So also be aware that r depend on t, theta also some unknown function of t. So let's do this change of variable. So very quickly, the right-hand side, we can replace each x and y with this in terms of r and theta. So the first equation, the right-hand side, the y will be r sin theta, the x will be r cosine theta, and 1 minus, you see x squared plus y squared, that will be r squared. So first equation, the right-hand side. And the second equation, the right-hand side, we can quickly get just to simply replace x with r cosine theta. The y is r sin theta. And 1 minus, and we know x squared plus y squared is r squared. So we get this. But what is the x derivative? See, if we simply put x derivative here, y derivative here, we cannot leave the system in this fashion because we're getting two new equations involving r theta. So we do not want to keep x, y as the unknown variables anymore. So to replace x derivative and y derivative, we have to differentiate the x. So from the first equation, we can see x derivative, right, will be, by the product rule, r derivative times cosine theta, and then plus, okay, derivative of cosine theta, which is negative sin theta times theta prime. And then this is r times r. So we have a product rule. So quickly we can get the x derivative. Similarly, we can find the y derivative using product rule. So y derivative, here the y prime means we're differentiating with respect to t. So here r, we differentiate with t. So r derivative times the sine theta. And then next we differentiate sine theta, which is cosine theta, cosine theta. So let's cosine theta, theta prime, right, by chain rule, and times r. So product rule for the y for this function, and then here we also have to use the chain rule, right, when we differentiate sine theta. So that's a composite function. And then we can just simply drop this is x derivative, which is on the left side of the original equation. So compare, this is x derivative here in terms of r theta, and that's y derivative here to replace the original equation. So the y derivative is also now in terms of r theta, or derivatives of r theta. So we have an equation. So this equation is the new polar coordinate version of the original system. So here you see the original system, right, in terms of x and y. That's the differential equation of xy. But now we have a differential equation of r theta. However, it doesn't look simpler than before. So we look at the newer version. It's still complex looking, and we need to simplify it. And what kind of form is more friendly? And we hope at least we get the normal form, if possible. For example, here, that's x derivative, y derivative. That's the right-hand side do not involve any derivatives, right, of the xy. So we hope we can have only r derivative in one equation and only theta derivative in the other equation. So that's our goal. How do we do that? So we just want to eliminate the theta derivative first. So the strategy is that we look at the polar coordinate version system, and we can do some operations. So the first equation, if we multiply both sides, so let's call the new system, we label the first equation and second equation. So if the first equation times cosine theta, and if the second equation times sine theta, that means each term of the first equation, right, both sides of the first equation times cosine theta, and both sides of the second equation times sine theta, then we add, and we will notice this term will be cancelled. Yeah, the term involving theta derivative will be gone, because if first term times the cosine theta, so if this one has a cosine theta times sine theta, if this one has a sine theta, cosine theta, you compare, they are the same with opposite signs, and then we add them together. The theta derivative, the term involving theta derivative, will be completely cancelled. So that's our strategy. We want to get rid of the theta derivative. So with that, we see the first, this equation times cosine theta, we get first equation cosine theta times another cosine theta, we get the cosine theta squared. And then add the second equation times sine theta, we get sine theta squared. And then the left-hand side, so the theta, the two terms involving theta prime will be cancelled. So we have only this term, but this is essentially r prime, because it is same as if we use trigonometric identity, Pythagorean identity, this is 1. So we have simply r prime. So we have this equation once we do this operation. So the left-hand side of a new equation is simply r prime. And what's the right-hand side? So we just continue to calculate. So let's write the right-hand side. Right-hand side, first equation times cosine theta. So we have r sine cosine theta. The second equation, okay, anyway, the first equation still, you multiply cosine theta, we will have a cosine squared. 1 minus r squared. So the second equation, remember, times the sine theta every term. So negative r cosine sine theta. And then plus r times the sine theta times another sine theta, which is the sine square theta, 1 minus r squared. So when we add the right-hand side after we do the product, and then we add the two equations together, then we see this will be canceled. And then since we can factor out the common factor, then after we factor out, we see sine square plus cosine square, which is 1. So the right-hand side becomes this equation. The left-hand side is simply r derivative. So by doing this operation, we can arrive a very clean form. That is, r derivative is on one side. The right-hand side happens to be depending on r only. So we get this reduced form. So here is our first equation after we do this operation. So let's write, which is this one, r prime equals r times 1 minus r squared. Now, how can we eliminate r prime? We want to get another equation. That is, the second differential equation will have something like this. The theta prime equals something, right? That's our normal form equation. So how can I get rid of r derivative using the two equations? So let's look at the two equations. If the first equation times sine theta, and the second equation times cosine theta. See, if the first equation every term times the sine theta, if the second equation times cosine theta, and then we notice the effect of doing that, we will create the terms involving r prime, right, in each equation. So we will have the same identical terms, two terms involving r prime. But then when we do a subtraction of the resulting equations, and then we can get rid of r prime. Okay, so that's what we will do. So let's do a subtraction after that. So this way we can eliminate the r prime. So first equation times the sine, second equation times the cosine, and then do the difference. So then we can see this part times the sine, that will be negative r sine square theta times theta prime. And the second equation minus r times cosine, so it will become cosine square theta times theta prime. And then we can see the left-hand side, right? After you factor out the common factors, you can use the Pythagorean identity, which is sine square plus cosine square, that is 1. So So once you factor out common factor, then this equation left-hand side will become very simple. And then let's look at the right-hand side. So the first equation, every term times the sign. So we will get r sine square theta. The first equation times the sign. So r sine theta cosine theta times 1 minus r squared. And the second equation times cosine, which is r cosine square theta plus r sine theta cosine theta times cosine, and then 1 minus r squared times, there's a 1 minus r squared. However, we're doing subtraction this time, so minus negative is plus, right? Minus a positive, then that's a minus. So we keep the sign correctly. So after the subtraction, this is the equation. So this current operation leads to this equation, but certainly we can simplify it using trigonometric identities because this equation is really, once you factor out negative r theta prime, what is left is just the sine square plus cosine square, which is 1. So the left-hand side of the equation, you see is simply negative r theta prime because this part is 1 by Pythagorean identity. The right-hand side, also we have r. When we factor out r, see the two terms, right? Sine square plus cosine square, that is 1. So we have only just r. And the remaining term, so when we add, they're canceled. So when you see the opposite signs, so this equation becomes very simple. So this equation is the same as if we divide r both sides. It's a theta prime is -1. Yeah, we divide negative r both sides. So theta prime is -1. And let's look at the reduced form. So the equation is now reduced. I will just keep the very clean form so we can see the normal form differential equations using in terms of r and theta. So here is theta prime equals -1. Now, so from, you see 1, 2, the equation 1 and 2, now we have two new equations. Let's call it 3 and 4. So this is a new equation. R derivative equals something. And this is another new equation. Theta derivative equals something. So we look at the two equations. Now it's a very simple look. Differential equations, at least we can find the relatively easily to find some simple form solutions. So let's put together the two current equations. The first one is r prime equals r 1 minus r times 1 minus r squared. the second equation in polar coordinate form. So this is a theta derivative equals -1. When we solve it, let's assume we try to find constant solutions for this system. That well, actually for R, for the first equation, so if the R derivative is 0, then if we let R derivative be 0, then we can find some constant solution. R has to be 0 or R squared minus 1 is 0. So that means we can find R is 0 or R is either plus or minus 1. So we, from the first equation, from the second equation, theta derivative is constant. So but we know these are very special type of solutions. Imagine R is 0 in the polar coordinate form. That's a point, right? That's 1 point, fixed point. When R is 1, that is a circle of radius 1. So we find some very special integral curve of the system, of this current system. The second equation, theta, when the theta derivative is -1, then we can find that theta has to be, because theta is a function of t, right? We do antiderivative, it's -t plus some arbitrary constant, integration constant. So let's try to look at some special solution curves. So far, we got some, when R is constant, when we draw these special solution curves, when R is 0, so that's a point, that's a fixed point. When R is 1 or -1, and we have a unit circle, because we're thinking of the polar coordinate. So we have a unit circle. That means a circle of radius 1. So the for this closed cycle, which is actually a closed integral curve of the differential equation, there are other integral curves, right? We want to discuss the relationship of other integral curves, whether they're attracted to this limit cycle or not. So look, we have a fixed point here and a limit cycle here. So suppose we have a solution curve that is inside the limit cycle. Let's try to discover the behavior. So if we have a solution curve starting from this point, and what will be the behavior of this? And don't forget, we have that equation that can help us know. So this is our current system. So suppose your integral curve is in the limit cycle. That means R is less than 1. So if R is less than 1, this part 1 minus r squared is positive, and times r, which is also positive, then the derivative is positive. That means r is increasing. R is increasing. Since r is increasing, and also the theta, you see theta is decreasing, right? Theta is decreasing. That means r increasing, but theta decreasing means the curve will go clockwise. So let's try to predict what happens. So we're going to draw a curve. We're going to draw a curve inside this, and it will be clockwise because theta is decreasing, and also r is increasing. So r is getting bigger and bigger. That means approaching the limit cycle. And what about an integral curve that is outside the limit cycle? So let's imagine there is another integral curve for the differential equation system, and starting at this point, then what's going to happen? It's still, we know the governing equation here. So if r is outside of the unit cycle, then r is bigger than 1. So this is certainly positive. R is positive, right? Bigger than 1. So this term, 1 minus r squared, will be negative. So the product will be negative. Product is negative, meaning the derivative of r is negative. So r is decreasing. R is decreasing. However, the theta is still also negative always. So theta is decreasing, meaning the curve will go clockwise, and r is decreasing this time. So let's go show the behavior of such a curve. So if it's outside of the unit cycle, the r derivative is negative, meaning r will be decreasing, will be closer and closer, right? To so it's yeah. So if we start from anywhere outside the limit cycle, then because the r is decreasing, so it's going to approach the depending on the speed, how quickly they approach, but certainly you can predict that it's going to approach the limit cycle. Yeah. So from inside or from outside the limit cycle, all the integral curves will be approaching the limit cycle. Then in this case, the limit cycle is a stable limit cycle. So based on our analysis, first we have found the fixed point and limit cycle. Then we look at some other integral curves, and their reaction to the limit cycle is that from within and from outside of the limit cycle, they are all attracted to the limit cycle. Therefore, here we have stable limit cycle. Okay, so we from the previous videos, I talked about fixed points, right? Whether they're stable or unstable. But today you see a limit cycle, which is a closed solution curve. And we can also do some analysis for certain problems and discuss stability.